nanohub.org.
Online simulation, and more for nanotechnology.
Dr. Cakmak is actually now at Grand Valley State University in Michigan. Today's topic is wave-based characterization. It's session number 10.
Thank you, Rob. Thank you, Peter. And I'll be talking from where Peter left, so how we can bring that into our classroom, all these expensive tools, how we can adapt into our lectures, how we can also give students some sort of an exposure, especially under the COVID times when many of the universities that have these tools cannot also give their students exposure to. While speaking about the exposure, I'll be feeding you with a fire hose today. So there's lots of things that I will go through, as usual, Bob would say. But the idea is, that what gives me the comfort is these are going to be recorded. And of course, I would never do this to the students out of mercy, but hopefully you can go back and watch that particular part, or I'm just going to introduce the main idea today about a simulation tool or something like that, and then you can adapt it in any way you like, and we'll be there on Monday to talk more about it. Okay, so first, the X-ray diffraction. So Peter already gave us a great introduction. So we'll go back at the summary about where it's going to be used. But the main idea will be today to use some tools in our classroom to teach the students the fundamentals or get them a chance to touch and feel what this X-ray diffraction is all about. So we have our atoms and we can draw that on the board and we can send the X-rays, right? So the wavelength is very small. We will talk about that. So we almost like it's showing it in like a ray phenomena, as you can see. And then we have these X-rays going back, reflected back in a way. But how are they going to be relate to this whole phenomena, the students at all levels, coming from community college or even K-12 up to the graduate level, right? So luckily we have really good tools, and that's what we also started at Penn State when I was teaching at Penn State over the summer, COVID summers, I should say, two past summers. I start by introducing the wave interference. These are just mere suggestions, and if you see fit, you can of course start from here too. And I have uploaded these items to you for your use on Blackboard. Okay, so once you go to week 10 here, so underneath session number 10, you will see these more information, and also Peter's video is here too. These two videos are given here too. Okay, the first one we're going to use will be wave interference applet. So this is coming from University of Colorado. Once you download it from their website, I gave you guys the link. You will be clicking on this applet here, and it's just a very simple thing. You don't need to install anything. It's just going to bring you to this. Why is it relatable to XRD? We'll see about it. It's starting with a wave interference phenomena, and the basic is like you can start from the water tap or with the lasers. So you just turn on the lasers, as you guys can hopefully see. It's a bit dark, I know. So we're sending, let's say, in the infrared or the red wavelength, okay? And we see immediately the interference patterns emerging, right? So this is what we call the diffraction patterns. And I would like you guys to just take a look at it. Some of you are very familiar, I'm sure. Some of it may be a bit more new for some of you too. But we have these diffraction orders, like this is the 0th diffraction order. We have this symmetrical first diffraction orders. These are the surviving waves in a way that are coming out as a diffraction pattern, as you can see, symmetrically occurring. Now, the wave will come, for the sake of our discussion, X-ray will come and will be reflected, if you remember, will be reflected from these atoms in a way, like these crystal structures, right? So it's going to be like we will have these sources represented by these waves getting reflected waves from the atoms, the crystal planes in a way, and they will be interfering too. So when we send a high wavelength, a large wavelength, like red wavelength, we see these diffraction patterns occurring. When the student immediately plays with the tool and brings it down to the UV, and they will immediately see that, oh, Now I have a different diffraction pattern occurring, and they can put a screen here. They can look at the screen more clearly so they can see the diffraction orders occurring. So maybe I can bring it to a more vivid color like blue. But the idea is now they're able to visualize. I hope you can see it. It's not just the zeroth diffraction order like I introduced and the first diffraction orders, but we have other diffraction orders appearing too. And the idea is, as the wavelength, let's go back. So I would like you to look at the occurrence place of the first diffraction order. Let's look at it. So it's like here. And if we bring it back to the red colors, and these diffraction orders, I don't know if you noticed, but it shifted up. So the angle. So if we put the screen here, and if this is our axis here, the angle, if I take a look at this angle here that I'm describing, I hope you can see it. So that's going to be getting larger, right? So as the wavelength is increasing, this interference pattern and these diffraction orders are also getting larger. The angle-wise, they're getting larger. That's one relationship that they can understand. The other thing is about this distance. So these are separated, right? So let's just fix the wavelength now, or the frequency. Now, and I might have a chat window. The separation between these two sources, which in this case will be our planes, right? Crystalline planes in the case of XRD will also be different. So as the separation distance is getting shorter, in this case, it's meaning that these diffraction planes are getting closer to each other, as you can see, right? So we see that the diffraction order is also starting to look at it. It's very small, so the angle is getting higher. So they're inversely proportional to each other. Let's just look at the other case. I'm just spreading them out. So the separation distance is really high now. And if you look at the first diffraction order again, I'm looking at all the time this angle here between this axis and the first appearance of this diffraction order. So it's much smaller, right? Just comparing the two. So in general, the student can have an idea, okay, if these planes, if these diffraction planes are close to each other, then the angle is increasing. There's a relationship. There's an inverse relationship between the two. And they can also understand the other thing with the wavelength. If the wavelength is getting larger, that angle is again increasing. So without doing much math or a lot of algebra, we can immediately let the students understand these two relationships. The wavelength and the angle are proportional to each other, whereas the distance between these two sources, in this case, it would be our diffraction planes, and the angles will be inversely proportional to each other. So this is going to be the main idea behind the XRD analysis too. So that was the starting point that came from University of Colorado, like I was saying. You can go to their website and examine their other tools too. But the important thing is to understand for the students that they get an understanding between the distance here, d, as we were looking at it, and the angle of the occurrence of these diffraction orders. They were inversely proportional to each other. Of course, you can do more analysis, more math can be involved, and you can show that on the boards, but I'm talking about in general, like this kind of a general feeling about these relationships. Now, I will take you to another source, and that's going to be located on NanoHub, and NanoHub's accessibility is increasing all the time. I'm going to recommend you to go there. If you don't have an account, you can easily get an account, and like here, it's just nanohub.org, and you can find it in one of them here, XRD tool from NanoHub. I think we're going to look into that. Before that, sorry, it's going to be the JMOL, the crystal analysis, crystalline planes. So that's going to be here, JMOL analysis. So I'm going to go to that. So I'm just going to write, after I log in, I'm going to go to my dashboard, and I just search for JMOL, and this is the tool we're going to look into. I launch the tool, and of course, they have a limit. If you go beyond the three simulations at the same time, they will just kick you out. Every user has only privilege of using three simulation tools at the same time. And I initialize this. Why is this good? Because they can see when I click on simulate, for example, different crystalline planes, different crystalline orientations, how the atoms are located. So here, for example, face-centered cubic is being analyzed. So I can, in 3D, just rotate it around, and I can look at the atoms, where they're located inside the unit cell. Right, so each one of these representing my atoms here. Some of them are inside, half of them are inside, half of them are outside. And you can, let's say, get some measurements here too. So I will also do that with you. But this is also telling us, okay, so we're looking at nickel in this example. So I also gave you some exercises that I carried out by students in these two past COVID years. So we were like looking into BCC and FCC, these crystalline orientations. You can see that they will have the atoms differently placed, and they can do simple math to understand how many atoms will be placed in each one of these unit cells, as you can see. These crystalline orientations will be repeated over the whole structure to represent the bulk material, of course. And another exercise, so I'm highlighting the exercises, can be about a real material like silicon. So if we look at silicon, going back to silicon, so if we select, it's a little bit of an older tool, so it might be, no, sometimes just getting, it's a little bit of a headache when switching between the materials. So we will switch to a real material. So we'll go to semiconductors. Silicon is selected, as you can see. And this time, yeah, so they are looking at the silicon's crystal orientation. And one of the things that I was telling the students to get a measurement, like here you can get some measurement between the two atoms, the smallest distance, and like you can see here, 0.235 nanometers. And I'm always asking the students, how can we be very precise? What gives us this kind of precision? They do the measurement, that they don't understand that we're like getting a super high resolution, right? This is like below the nanometer angstrom level and lower than that. So, and they immediately think about, of course, the different characterization methods, and like Peter talked about, they think about XRD, and we'll go into that too. So this is how they could do a measurement here. Look into different crystalline structures. Doesn't have to be just silicon. There are a lot of other options available, and also metals too. Yeah, so that was the shortest distance we were looking into. And they can also look into these planes, crystal planes, like we were saying, 211, 010. These are going to be very important for the sake of discussion of the XRD. And there's another great tool coming from MyScope. So I gave the link in the PowerPoint, but you can also look into that from our website here. So MyScope training, I'm just going to click on that. They have a great XRD simulator. If you click on that, okay, and this is our XRD tool, like Peter was showing us a second ago. So if we look into our specimens, like let's say I'm going to look into aluminum, why not? And then the doors will open. So my specimen will be placed. And then I close the door. My X-ray source will be here. And this is going to be my detector, of course. And I will start applying my source. And then my scan settings will need to be determined. Like these are going to be the angle scan settings, the starting angle and the ending angle, and the step sizes. So let's say for a quick scan, you can do a scan with the students, and then they get an understanding of just a little bit of a feeling. Okay, now we see the peaks occurring, and these are coming from the of course, the crystalline orientation of aluminum. So they can combine this with, say, JMOL and the tool that I showed you and look at aluminum's crystal orientation and try to understand where these angles came from. So in a higher degree, they can calculate these angles themselves and try to see if these angles are really found out at the locations that this tool is giving us. So they can do all these kind of tricks. And let's look at something else. For example, glass, which will not be in a crystalline orientation. It's an amorphous material. So if we, not talking about quartz, of course, and if we set the angle ranges again and hit the start scan, so yeah, we get a not that kind of a nice peaks anymore, as you can see. So yeah. So they can understand the differences between more crystalline structures and more like polycrystalline or amorphous structures. So we have other options here too. They can look into sand that I would also suggest. Anyways, going forward, just to introduce you more and more. So yeah, like I was saying, they can look into polycrystalline structures, which will widen up these and also give you different X-ray diffraction patterns, not just like single points, but like these kind of connected lines because of different crystal orientations that we can get from these polycrystalline orientations. And at higher levels, they can also look into, like I was saying, different these crystal orientations and these different crystalline planes, Miller planes, and do a little bit of math and try to understand, say, using another one of these nice NanoHub tools. And this is now here, XRD tool from NanoHub. I'm just going to click on that. And probably it's going to tell me to terminate one of my simulation tools like we saw before. Let's give it a try. This is a great tool, by the way, because it shows you the whole code as well. Now at this age, the students are encouraged more and more to learn more about the coding, of course. So let's start with the basics. Let's look into the X-ray diffraction pattern for BCC and FCC. These are different crystal orientations. So this is written in Python, and all the students that they can go through these codes. And if they learn a bit about the Python too, they can duplicate these, or they can just simply hit the run. So at an earlier level, they can just hit the run. And at that point, it will automatically create an applet like this. This shows us the lattice constant and the X-ray wavelength of the source that we're applying from. And we have the FCC structure, for example. Now, this is to the 2 theta. That angle is multiplied by 2. And you can see different peaks occurring at different locations. Of course, this is a very simplistic tool, so it's not giving us a intensity-wise distribution, so everything is normalized to 1. So it's not the case. We can emphasize that to the students, but just for the sake of keeping it simple, we're just looking at these different crystalline planes and different peaks that we can attain. And like I was saying, with a different, higher level of a class, just a little bit of a higher, we know this famous formula. Every one of us know these famous formula when we're working in the field of XRD. This D is going to be about the distance between these crystalline planes that we were looking into. I mean, these Miller planes. We'll have information about that. This theta and that D was also had information about those 2 interference, the distance between those 2 sources. Do you remember that? The simulation that we did with the lasers? Yes, so the student can understand, okay, so D is related to the wavelength, the source of the X-ray that is hitting the structure, and theta is also related to the wavelength too. So we said that wavelength is proportional to that angle, and we said that D separation was inversely proportional to that angle. So, okay, so they can understand it from the math, but if we are avoiding math, we can also, like I was saying, show that to the students using these simulation tools. They can plug in the numbers, say for one of the structures with a certain lattice constant. So you can give them all the lattice constant, the source of the emission, and they can figure out, but using a simple math, the angle that these peaks to be expected to be occurring. And that angle, if you look at it, 17.5. If you multiply that by 2, is going to occur at the same, so 35 degrees, as you can see. So they can do just these kind of little tricks to understand it in a little bit more depth. And yeah, like they can do it for FCC, but they can switch to BCC with a different lattice orientation, and they can retrieve different peaks too. Now going back, there's one other thing that I enjoy doing with the students. They can look into an alloy. So I'm just hitting the run button till this arrives. So this is made out of, let's look at our notes, 2 different metals, nickel and copper. This is an alloy made out of these 2. So we're using XRD to understand the percentage of nickel versus copper. So we know that nickel's lattice constant is slightly smaller than copper, okay? And based on that, we can give to the students, okay, just concentrate on one of these peaks, and we can give them, okay, so my expected angle is, say, 74.6. Now let's go to the application. So this is the answer, of course. So this is full nickel now. The alloy ratio is 0, meaning that it's made out of nickel. And this is completely made out of copper. Okay, so if they look at one of these, only the 2 to 0, so this is 74 with a smaller lattice constant, okay, and with a higher lattice constant, that was 74. With a smaller lattice constant like nickel, it's going to become 76. So you can see the inverse proportionality again coming into play. And without telling to the students what the proportion is, we can just say, okay, play with it and find me the ratio. The correct answer will be, of course, they will have to scroll through and do a little bit of thinking, because they have to think that, okay, so it should be closer to one of them. The higher A gave me a smaller angle. The smaller lattice constant gave me a higher angle. So if I'm closer to the copper, 74 degrees, so it should be more closer to the copper. So 75% of copper and 25% of nickel. So that would be the answer. I hope that makes sense. And yeah, so it takes a little while to catch up, but yeah, they can scroll. That would be the Cayman methods for the students, but they can do a little bit of more thinking and arrive at the conclusion that it will be closer to the copper side. All right, so after having introduced you to that tool too, okay, another great tool. Now, if you like to look at a more realistic, like with the intensity involved and also the broadening effect involved, because our structures may not just be like bulk, large grain size structures. Grain sizes meaning that we have like a larger, almost like a single crystalline structure. That is having a larger grain size, but we may have smaller structures like nanoparticles. Even as you can see here, we're looking into some nanoparticles, really tiny structures. In that case, our crystalline sizes are becoming almost closer to the grain sizes themselves. So we are going to be in trouble. And the students can understand that, because if you look at the nanoparticles, if you look at the examination under XRD with the nanoparticles, those peaks that we were used to seeing as very sharp peaks are going to be broadening up because of the fact that these are getting very close to each other. The nanoparticles already getting very close in terms of the sizes, like you can see 2 nanometers. So that's going to be an issue for us. And that's another tool here, XRD with the amplitude. So if you go in there and launch a tool, now we can identify the problems that can be coming from the looking into like more bulk materials or like these kind of nanoparticles under XRD2. I hope this will come soon, show up soon. Yeah, that's another Jupyter notebook kind of coding involved with Python. I'm just hitting run to come to the conclusion here. Yeah. And let's generate the plot. Yes. So now we have a little bit more control over the temperature, the crystal thicknesses. So if these were already things that we were parametrically playing with, lattice constant. But if you look at the crystalline thickness, a crystal light thickness, and if we just make it like 2 nanometers, you see the broadening here. This is the nanoparticle case. Now, if I look into more like a bulk material, you see we arrive at the narrow peaks again. Okay, now XPS, we start to another discussion. Now, we're going to again send X-rays to our samples, but this time we're going to extract photoelectrons. So as one of our attendees was saying, X-rays based on sending the light wave, and then we're going to extract these orbital electrons, and these extracted electrons will have incredibly important information to determine our material, their characteristics, what they are, etc. It all starts with the photoelectric effect. So I did also upload a applet photoelectric effect here. So if you click on that applet here, okay, maybe I don't need to. It was explained by Einstein. It was found out by Hertz in 19th century. And this is also coming from University of Colorado. So this is a very simple tool that shows the students the main idea of XPS. So let's just start with the tool. I will send some light, some intensity of light. So I'm just shining some light onto a anode here, and I'm getting the light from the material. Sorry, in this configuration, it's turned to be a cathode, but it's not super critical. So we're extracting some electrons here with the intensity. So as I increase the intensity, of course, all right, so I'm gonna start capturing more of these electrons. I can show this in terms of the intensity is light, show photons like this. All right, bombardment. And as the intensity is dropped, of course, I don't have much going on. So the current that I will get within this, between these two plates will be determined by the light intensity, of course. So that would make sense, right, for the students. So we're sending more of these photons. We're able to give more energy to the plate and extract more electrons from the structure. So that would be obvious. Now, and we're eliminating sodium plate, by the way. And if we go to another wavelength, so instead of giving them, you see we have another control here. This is now 400 nanometers. Let's set this intensity to something in between. So we're giving 400 nanometers. This will be important because the photons, in order to extract these electrons, they will have to give some energy to the source, right? To the plate, the atoms, to work against that binding energy of these electrons in a way. We can start discussing about the binding energy. If we give them less energy, those photons, like the yellow light, what's going on? The plate, we cannot extract the electrons anymore because the wavelength is increased. And if we explain to the students this inverse relationship between the wavelength of the light, of the photons, and the energy, which are inversely proportional. So we're essentially giving less energy to the plate and no electron is extracted. Again, going back, if I go down, of course, I will be able to extract more electrons with the same intensity. So I have a way to control the number of electrons that I can extract. I gave lots of case studies here for you guys to look into in these slides. We may not do all of it, but oh yeah, one other thing, say we can switch from the sodium to a higher atomic number plate like copper. So you can do it from like, say, from sodium to copper and look at the results now. So the copper has a higher atomic number, so it will require more energy to extract these electrons. So maybe something just to start the extraction with. I'm setting the wavelength a little bit lower. All right. Now, if we switch to sodium back again, yeah, you see now with the sodium light material, lower atomic number material, we can extract more electrons. So the higher atomic number materials will require higher binding energy. So in a way, they will like their electrons more. They won't extract, you won't be able to extract those electrons easily. Moving forward now, yeah, this is a more like a realistic picture of the XPS in one of the labs. But of course, like we were saying, we may not have the luxury to get our students into this kind of a characterization facility to examine the samples, where we generate an X-ray and shine it onto the material, like you can see here, silicon dioxide sample, and we can collect those photoelectrons. And this is a more, again, professional look into the X-ray under ultra high vacuum, like one of our attendees was also explaining. We generate the X-ray from the X-ray source using an electron beam filament, and then shining that into a plate itself to generate the X-rays, and then we shoot it to the samples and try to extract the electrons and try to analyze the results in the end. Okay, so if you can't go to the lab, at least we have a solution from NIST. I'm sure everyone is familiar with NIST, National Institute of Standards and Technology. They have a great simulation tool called CESA. So all you need to do is here, I gave that to you too. You can download CESA from here. So all you need to do is to go there and choose your operating system. And I chose Windows, for example. You will need to fill in some forms there to give them a little bit more like a survey kind of thing. Why are you using it? What level are you going to use it, etc. Some people are really using it for research, and it's a really research tool. Look into CESA. I already downloaded and installed it on my computer. All right, so the first one we're going to look into is a survey result, which is like a quick and dirty kind of a scan. So we will just look into copper. So hit sample here. Every time it pulls it into the other screen. I'm sorry about it. I'm pulling it back. No, now we have silicon substrate. As you can see, it will tell us. You can click at layer, and this time, instead of silicon, you can switch to copper, and that switches that to copper. You can determine the thickness of copper layer, so like say 10 nanometers, 100 angstroms, okay? All right, now if you click on peaks here, all right, and these slides are already guiding you, you will see a lot of peaks here, like, yeah. Some of them will tell us information about like some familiar things like P, S, those orbits, right? And but some of them may not be so evident. So we have a combination of these Ozgur peaks here with these other peaks that we will be more interested in, like the 3S, 3P peaks that we will look into today. Okay, so you can keep them all. You don't have to worry about the distinction, because the tool will tell us like which peak is expected to be at which position. So you will be able to distinguish between the peaks. Okay, but you can also cancel them out too. So it's up to you. Now, if you go to the spectrometer here on the other side, now we can set the boundaries, like say from 300 electron volts to 1.2 kilo electron volts. Now this is going to be getting the extracting those photoelectrons with certain energy. So it's going to search from the electrons from, say, in this orientation. Let's keep it like that for this case, from 600 electrons to 1.5 kilo electron volts, as you can see. Okay, so and we can go to the source. So if you click onto the source, you can choose different sources. This is the most commonly used source, aluminum source, or you can choose magnesium. So there are options. Now, this is going to be the source that will have a certain incident energy, as given here, 1.4, almost 1.5, 1,486 electron volts, as you can see. This is the incident energy that we're going to shoot the samples with. And next, let's just go to the simulation. I'm just clicking on the simulation and start simulation. So it's going to give us a survey result, as you can see here. So, and we can look into our peaks together. So here it's the peaks will occur. So like you can see, we have everything about the copper 3p and 3s, those peaks are occurring. So these are the electrons that we're extracting from the material, okay, from the certain orbit of the material. And this here is showing us the energy of the electron, the kinetic energy, like they call it, of the electron that just got freed up. Okay, so that's good, but how can we use that in our classroom, just as an example? So we know of course, the electron orbital configuration of copper, simple material, and we know the energy levels of these electrons here, like you can see the labeled. So we have the binding energies labeled here. So as we move on down the ladder, down to the core, so the binding energies are increasing, and those valence electrons, as you can see, are very weakly bound to the atom. Okay, so now you can do a simple analysis with the students, like the following. Say, going back to the survey results one more time, and looking into these peaks, you can say, so if I zoom in here, we have an incident energy of this much, say 1,486, and we have a binding energy that we were expecting. Okay, so where do we know that? Well, you can just Google that get extracted from Wikipedia, etc. They're all well-known energy levels, thanks to quantum mechanics. Say we'd like to get 2p6, those binding energies, and all you need to do is go and put that into your EB, the binding energy value, and you know the incident energy that you're sending, you know the binding energy. Now, if you subtract those two, because you're giving that much of energy to the copper material, and you know how much that copper material likes to keep that electron from the binding energy, right? And you can get, just by the conservation of energy, subtracting those two will give you the kinetic energy of the electron that you're extracting here, that you're measuring here. And if you look at the peaks, and like say one of them, say incident energy is 1,486, and you have the binding energy is 1,097. So the kinetic energy is given to be 389. So it's really in here. Okay, so this is corresponding to this peak, for example. Okay, so that's going to be the 2s photoelectron. So you can go back to your analysis. Oh yeah, that's really the 2s electron. If I plug in the numbers, so that's satisfied in here. So the 2s electron, it's going to be really out of the range here, because we set it in the spectrometer as the 600 electron volts as the shortest range here. If I pull it down to 300 electron volts, we would be able to see it that too. Anyway, so these kind of simple analysis can be easily handled. Other than that, now you can, of course, instead of copper, you can switch to a different material like palladium, and do the whole thing for palladium. All right. Now, what we can see here is, of course, associate these different peaks. They extracted photoelectrons, but we can see the spin coupling, so more evidently. So I gave a little material for you to read if you're interested, of course. But now the angular momentum coupling for a heavier material like palladium will be more evident. So we will be able to see these the peak separations, say between the thanks to the spin coupling and the angular momentum coupling. Again, going back to a little bit more advanced quantum mechanics, but of these two peaks more evidently than copper. So in a more advanced discussion, so you can talk about that in your classroom too, that you can see the 3/2 and 1/2 at the same time here. Right, so they're probably corresponding to these two in here. Yeah, those little two peaks there. So I don't know if you can see it with my mouse, name is given here, and the energy level is going to be also given there, or no, it's also given in here. All right, so what else can we do? We can appreciate what kind of a surface characterization method this is. So we can keep our 10 nanometer palladium, but then we can start adding copper. So I'm just adding another layer and replacing that with copper. So my copper could be like first just 1 nanometer, so which will make it just 10 nanometers. So what is this now? I have a 1 nanometer of copper at the top. I have palladium 10 nanometer underneath, and I have silicon underneath that too. So the students might just be like asked, are you expecting to, which peaks are you expecting to get? Like which associated with which material? Because once you generate these photoelectrons in here, inside this bulk material, they're gonna they're gonna be exhausting their energy. So the escape depth of these photoelectrons, that's what we call it, will be very, very short. That's why XPS is really like a surface characterization method. They can start to see that with their own eyes, analyze it with these parametric scans. So like 10, just 10 angstrom will give us just 1 nanometer. And if you simulate this now, we can ask the students, are we expecting to see, if you look at the results that I previously captured in here, so I think I also did it in the logarithmic scale after a while too, but we see the copper peaks, of course, evidently, because copper is at the top. Yeah, copper is at the top. I can see the copper peaks very clearly. Those are the copper-associated photoelectrons. But how about the palladium that we were extracting previously? So I guess these are the palladium, and these are, where's my copper? Copper is around 400. So it's, again, going out of my range. I didn't set it right, so probably I should have said, let's do it very quickly. So let's go to 300 and start the simulation again. Okay, so these are now, yes, these are my copper peaks. I don't know, closest peak, you can see it. These are copper peaks. And I can see the palladium peaks in here. Yeah, they're small, but I can still see them. Now let's do it for thicker copper at the top. So what kind of a thickness did I select? 2 nanometer. We can go to a bit more, 5 nanometers. So let's just say 50 angstroms at the top and starting the simulation again. So this is the area where we were getting those palladium peaks. Now they disappeared. They will only appear again in the logarithmic scale, so you can see. So it's really like even 5 nanometer is, we're losing the touch with the underlying material. So that's an important observation that the students can get. One other thing is about the depth profiling. So they can understand, okay, so if we shift this, tilt this sample, like we have copper and palladium, but based on the angle of incidence, so we have an incidence of the source, let's say initially at 90 degrees, and then we have the detector at a certain angle, and they can all be set here, the configuration, like you can see here. It's the, it sets by default set to 60 degrees, the detector at 60 degrees. We're sending it at 0. So you see that they're not aligned with each other, right? So there's a misalignment there already. But if we make them aligned, in other words, if we go there again, configuration, if I set this to 60 slowly from 0 to 60, if I scan that just to speed it up, I will show you the results. So this is my orientation. And as you can see here, at this point, when everything is nicely aligned, I can extract more results because my depth now that I can reach and extract these electrons, those photoelectrons from, will be higher. My likelihood will be a lot higher. So I can at least get some more information from the underlying layers. But if I start to tilt that whole sample together, as you can see, I will now dissipate more of my time inside the first layer, right? So here it's more evident. Now I'm only just seeing the first layer. I hardly can reach the second layer. Those electrons will be lost. So if we align them together in this configuration, 60 to 60, in other words, like this is now what we get from palladium at 0 degrees. This is now what we're getting at 30 degrees. You see the evidence increment between the peaks, right? So as I'm starting to align those two, now if I go to 60, it's more and more aligned. So I can get more information from the palladium, which was underneath. So I can start to get the underlying layer underneath the copper, which was 1 nanometer only. All right, what other things that I can do? I can look at the chemical shift, which will give me information about the chemical compositions and inside, like polymer analysis, etc. So I can do, instead of just silicon, for example, I can delete these layers. I know the peaks of the silicon, but instead of silicon, I can, right, there's a certain syntax for this. I can say that this is my oxide right now, and I can determine it to be a stoichiometry of 1 to 2, of course, and I hope this will like it. Okay, yeah, it did. Now it divided it in between silicon and oxide, as you can see. And if you look at the peaks, it will bring in me my oxide peaks together with the oxygen, of course. And it's doing its best to compensate or try to integrate both of them. And if we look into the peaks, now because of the fact that it's now oxidized, silicon is not silicon anymore, but it's oxidized, it went into chemical reaction, right? So the silicon material will not give me the same kind of peak locations because now it's under the influence of the oxygen atom too. So if we look into this configuration here, we expect to find the carbon at the single location, right? Ideally, carbon is carbon. But since we have this kind of a complicated reaction, and I am getting like carbon in reaction with hydrogen here, hydrogen there, oxygen, and fluorine here, depending on the electronegativity, how much the other material, the atom, likes it, it's going to be harder. The binding energy will be higher. So for example, extracting photoelectron from this carbon here will be more difficult because fluorine likes it more than hydrogen in here. Likewise, my peaks will be shifted because now oxygen will like those electrons that I'm trying to extract with the generated X-ray that is hitting the sample. So just to speed it up and let Neda take over in a bit, you can also simulate these and just to let you know, you can use this chemical shift browsing. So you can go to that particular peak you're interested in, let's say 2p 1/2, and you can click on the browse data sheet. And there are lots of like databases here. You can use the one that you find suitable, like say for silicon dioxide. I like to use this one here and select the chemical shift so it adapts. So we can now see that, let me just show you the results. Based on the electronegativity, as we're going back more and more to the 7A, right, on the periodic table, electronegativity will increase. And if we follow those steps, now this is the Bayer silicon. I get those 2p states at around 1154. That's the free electron energy, photoelectron energy, kinetic energy that I extract. If I oxidize a sample, they go down to 1149. Now we examine those two. Now these are the electrons that are just freed from silicon. This has more energy from the Bayer silicon. Why? Because this did not oxidize. This one has lower energy because this got oxidized, and meaning that oxygen likes it more. It doesn't want to give it, so you have to dissipate more energy with the slightly increased binding energy. So now you see that it increased up a bit, so that my free energy that I'm extracting, the photoelectron, that dropped down slightly. So I will again continue by showing you how we can integrate into our classroom all the information about FTIR and Uvvis. So just like the others, I have an app here that I uploaded on Canvas for you people. That's going to be called Molecules and Light. We have different variations like microwave, for example. So we have carbon monoxide under investigation. So microwave-wise, we can interact with this molecule, as you can see, and water, right? So that's how we heat our pizza, how we cook our materials with the applying microwave to the polar molecules mainly, and it doesn't interact with oxygen, of course. And we can go to infrared, like Neda was explaining. So now we can see if it will interact with the infrared light. So we can select another one. So you can see that now it comes in and it starts to vibrate, just like those little springs that Neda was explaining. You can do that for visible and ultraviolet too, but without losing time, we can just. So when I talk about FTIR, infrared spectroscopy in general, just like Neda was explaining, we have to think about those masses and the springs and how we can like resonate these bonds, right? So all these different bonds will have a different resonance frequency, and the students get to know about these even at the level of high school. Like the frequency is proportional to the spring constant and inversely proportional to the mass. But just to do another review, and I uploaded that under mass and spring spaces. So this app will show to the students, maybe stretch. So let's say you have 250 grams in here. So that's going to give us that much of a stretch here. I think I should be able to, resonate it a bit, maybe. No, it doesn't. This one did not. Sorry about that. Or yeah, if we increase the spring constant, you can see that the stretch got to be smaller and smaller. But if I loosen it up, this is, of course, very well-known information. There's another one. I will try to upload it that can also resonate too, but like with another mass that's under investigation, they can look at the vibration too. So I'm trying to vibrate it a bit. It doesn't do much, but let's just look at it quickly. So if I increase the spring constant just by manually trying to vibrate it, you see that it vibrates very quickly, right? So that frequency will be high. But for the loose guy, let's say the spring constant is small, that vibration is much less pronounced. So like you can see here. So that brings us back to the same kind of discussion that we initiated. Spring constant is proportional to the frequency of vibration. In this case, we're talking about infrared frequencies. So going back to the same kind of discussion, so we are sending infrared light this time, and then the material is absorbing it and consuming that and using it to vibrate the bonds and dissipating that in terms of those kind of actions. So one thing that the students always ask, of course, like, okay, so I have like just I showed you, so you can excite the bond, but it doesn't resonate. So the one on the left is not at the resonance frequency, but the one on the right does resonate at the resonance frequency, and it does do that very violently, of course. It will not break the bonds, but it will be more apparent. So the light will be really like trapped in there at that particular frequency, because now you're really resonating with the bond. So this will be like a nice fingerprint analysis for the like what kind of material we're looking at. We can get a good analysis out of it. So it brings us back to that famous Tacoma bridge, right? So whenever the students want to think about the resonance frequencies, just like the other springs, so these bridges, they also have the resonance frequencies too. So if we look at, say, for these different bonds, we have the oxygen, hydrogen occurring at different points, meaning that they have different spring constants. Their motion is also altered differently. So that is all good. So the students get to understand, okay, so if I have if I'm sending the light, so these bonds will give me at different locations, different peaks, but where does the Fourier transform come into the play? But before doing that, let me also show you this other thing that I uploaded. It's in a zip folder, but if you unzip it and if you double click on it, this is very joyful to analyze. So you can study this and this gives you a chance to look at, say, I want to look at isopropanol. So you click on isopropanol, and let's say you want to choose, let the students choose, oh, where was oxygen, hydrogen again? Of course, this is at this kind of wave number. Where was carbon, carbon? Oh, carbon, carbon is at this wave number. Those kind of analysis can be done. And the student can even do another compound and can understand, okay, so all these will give me a different response. That's all great. But where is the Fourier transform coming in play? So that's harder to explain to the students, but it's again a wave-based phenomena, an interference wave phenomena. And as I always emphasize, probably Fourier is the #1 person that I admire as a mathematician. He's the person that enabled a lot of technology coming into reality. And I uploaded a simple MATLAB code, if you guys are familiar. If not, that's not super critical, but you can look at what I'm doing here very quickly. So if, let's say we have a very simple signal, let's say something like this. That's a combination of two signals. So I'm just gonna plot the original signal here. If I can, of course, within the given amount of time. That's going to be very quick, but yes. So I would like to just look at the original signal. I'm just missing one parenthesis here. Okay, so where did it bring us? All right, so looks like I did not do it right. But anyway, so let me just go back to because we don't have much time, so I'll just wrap it up here. Yeah, where's frequency transform coming into play? So here we have two frequencies that you cannot notice, but these are at two different 30 hertz and 200 hertz. And I'm adding some random signal on top of it, coming at different frequencies. So you cannot notice which one is which, right? You cannot see those nice periodic signals at 30 and 200 hertz without looking at the code. It's in here, sine 30, sine 200 hertz. So they're given in there. But Fourier transform enables us to see those signals. How? By doing a Fourier transform. So when you do that, it will show us, so just to give you an idea, of course, a lot of us are familiar, but then you can fingerprint that into not again time domain, but now this is carried to frequency domain, and you can fingerprint that, oh, that's my 30 hertz. Oh, that is my 200 hertz. So just like that, we get its spectrum from the interference phenomena coming from the wave acting on the material. But then when you take this Fourier transform of this wave phenomena acting on the material infrared light, you can go back and analyze this time in the wave number domain, which bond am I looking at? Is it like vibrating at this frequency or that frequency? You can immediately analyze. Yeah, there's a lot more to be said about it, but we will leave it at that point here. Now, very quickly about the Uvvis in a few minutes here. So Ned already explained how it works. We have a reference sample and a sample here. The material absorbs the light as it's propagating. We lose the intensity. And then like these kind of discussions are always one of the things that are very high research area in the field of nanoparticles, for example. So like we look at the solution with nanoparticles, it changes its color. That's all about the Uvvis, ultraviolet spectrum analysis, because you send optical spectrum light and we see that it shines us back those nanoparticles inside the solution, gives us a red color. And it's just like these nanoparticles are like little antennas. They resonate at certain frequencies. Like they look at, say, I would like to get some signal from this frequency, and I resonate at that frequency. Say 1.2 micrometer does not resonate, but when you switch to 600, it resonates. That particular wavelength excites this nanoparticle. And if we look into the simulation tool on NanoHub, that's really nicely explained. So this is a great tool that you can utilize the Nanosphere Optics Lab, because a lot of us are synthesizing nanoparticles in our labs, in our institutions, like these kind of little nanoparticles, say gold nanoparticles, and we're sending the light, and this is now getting the ultraviolet Uvvis measurement. Okay, so it says efficiency, the extinction cross-section, you can read it as absorption, okay? So it's not one-to-one the same thing, but wavelength and absorption is here. These nanoparticles absorb the green color, okay? You can see the peak occurring here, and they also absorb highly the blue color. What is left is the red colors. It's not touched, so that's why they become red. And you can do it for, say, silver, restimulated, and see that silver will absorb a different, completely different color, and that's the main difference why, and thankfully to the Uvvis, we get a different color from the silver nanoparticles. And I promise this is going to be the last thing. This just wanted to also share that with you. This is the Uvvis analyzer on NanoHub, and that's the thing that also Neda was talking about. So this is also very fun to work with because the students can now look at different compounds like pyridine, for example. They want to look at pyridine, and this is the molecular structure. They look at it. It's like, say, forensic files for at the molecular level. So they look at it and they see that, okay, I have these bonds here, and I can look at the Uvvis absorption spectrum too. They collect these particular absorption wavelengths, absorption peaks, and pyridine is like that. Now, if we say the culprit went to an area that had benzene in it and now restimulated that, now benzene can be coming from anywhere, like if you went to a gas station, you get some benzene from there. You see the compound structure is slightly different. So let's compare the two, like slightly different, and that will show itself in the absorption spectrum. So we do not have that particular peak in there with the benzene. This is pyridine, this is benzene. So they absorb different, they give you different peaks in there. And as a final slide here, just to summarize, we first started by sending the X-rays, and XRD gave us critical information about the crystal structure. So as I was saying, it was an interference phenomena, and Peter showed us very nice sample preparation and how the tool looked like in general. We can get crystals, orientations, crystal sizes. We can get internal stress if there is a stress embedded inside my material after the fabrication. We can get an idea about composition. Remember the alloys that we were looking into. With XPS, it's a very surface level analysis, but we can still get stoichiometry level analysis. We can get elemental composition, so we can say, what are we looking at? Is it copper's electron? Is it the other electron from, say, palladium? We can get stoichiometry. We can get electronic and chemical states. With the FTIR, we identified the bonds, and we can generally analyze organics and polymers with the FTIR. And with the Uvvis, we can send it to the ultraviolet visible spectrum light and look at the absorption spectrum this time and see where the light will be absorbed in materials. With that, we will conclude